Hello my dear students, good morning to you all. So, in this session I am going to start with the reactions and reactivity of phenols. So, this is the chapter 4.1 which is prescribed in unit 4 under paper 3. Okay. So, the first unit which I engaged these many days was thermodynamics. So, that was unit 1, and another unit which I am going to explain about in this paper 3 is about reactions and reactivity of phenols. Okay. So, you all know what are phenols. So, in organic chemistry, so these phenols, sometimes they are also called as phenolics. So, these are a class of chemical compounds which consists of one or more hydroxyl groups, that is hydroxyl groups means OH bonds. Okay. So, these OH bonds will be directly attached to aromatic hydrocarbon group. Okay. So, such type of compounds are called as phenols or phenolics. So, to go to introduction part, so as I said, so phenols can be defined as, so phenols are the organic compounds containing OH group attached directly to the aromatic ring. Okay. So, the aromatic hydrocarbon group, it can also be called as aromatic ring. So, the OH group, as I said, OH groups are called as hydroxyl groups. So, these hydroxyl groups will be directly attached to an aromatic hydrocarbon or else to an aromatic ring. So, such a type of chemical compounds are called as phenols. The simplest is a phenol which is called as a C6H5OH. Okay. So, if you imagine the structure of benzene, so this is the structure of benzene. So, here in place of one hydrogen, or I can call it as proton. So, C6H6 is the structure chemical formula of benzene, right, C6H6. There one hydrogen will be replaced by OH group. So, that is why C6H5OH. So, this is the simplest form of phenol. So, phenolic compounds are classified as simple phenols or polyphenols. Okay. So, that we will see in my next slide based on the. So, this classification of phenols is based on the number of phenol units in the molecule. Okay. So, based on the number of phenol units, so we can classify them. So, to understand the structure of phenols with the positions, so you all know that we start numbering from here, since this is the OH group, hetero group which has been attached here. So, this will be the 1, 2, 3, 4. Okay. So, when the substitution is present in the second group or in the fifth group, then it is called as the ortho position. Suppose if it is present in the third group, okay, so third or fifth, so such type of sorry, this is first, this is 1, 2, 3, 4, 5, 6. Suppose if it is present in second and sixth, then it is called as ortho. Suppose if the substitution, that is OH, okay, so hydroxyl group, if it is present in the third substitution or third carbon and fifth carbon, then it is meta. Okay. Suppose if the substitution of OH is in the fourth position, then we call it as para. Okay. So, this you already know. Okay. So, this is the second position is called as ortho, third position is called as meta, fourth is called as para. Okay. And fifth is called as meta and sixth is called as ortho. Okay. So, in this way the structure of phenols with the position can be understood. Okay. Next, as I said, so the classification of phenol compounds is very simple, that so how many hydroxyl groups are present. Okay. So, it can be classified as phenols or polyphenols based on the number of phenol units in the molecules. Okay. So, as I said, they are classified based on the number of OH groups attached to the aromatic ring as follows. So, the first classification is monohydric phenols. Okay. So, as the name itself says, mono means one. So, here one hydroxyl group will be present. Monohydric, hydric represents hydroxyl groups, mono represents single, one. So, one hydroxyl group is present, then such type of phenols are classified as monohydric phenols. For example, so as I said, a simple phenol. So, this is a simple phenol C6H5OH. Okay. So, such a type of phenol is an example of monohydric phenols or orthocresol. Okay. So, where one hydrogen or proton will be replaced by methyl, since it is substituted at the second position, I call it as a orthocresol. Suppose if this methyl group is present in meta, so then it is called as metacresol, and if this methyl group is present at para position, that is fourth position to the aromatic ring, so then it is called as a paracresol. Okay. So, this is how the first classification is made based on the number of OH groups attached to the aromatic ring. Okay. Next classification is about dihydric phenols. As the name itself says, di means two, hydric means hydroxyl groups. So, dihydric phenols means in which two hydroxyl groups are present. Such type of phenols are called as dihydric phenols. For example, 1,2-dihydroxybenzene. Okay, so this is the first position where hydroxyl group is present. So, 1 and this is 2 where hydroxyl group is present. So, that is why 1,2-dihydroxybenzene, and it is also called as a general name is catechol. Okay. So, it is one example for dihydric phenols, and in the same way if this OH group is present in meta position, so then we take the numbering of the hydroxyl group is very important here. So, since one hydroxyl group is present in one position and another one is present in third position, that is meta. So, I call it as 1,3-dihydroxybenzene. Okay, and it is generally called as resorcinol. And the third example for dihydric phenols is suppose if the hydroxyl group is present in the fourth position, para position, so then it can be called as, so this is wrong, so correct it. So, this is 1,4-dihydroxybenzene, and the general name for this is quinol. Okay. So, this is 1,4, this is fourth position, this is not 5. So, this some typo mistake is there. So, this is 1,4-dihydroxybenzene. Okay. So, this is the second type of classification what we are going to see, and the third is trihydric. Trihydric means, as the name itself says, tri means 3, hydric means hydroxyl groups. So, 3 hydroxyl groups has to be present here. For example, 1, 2, 3 trihydroxybenzene. So, this is 1, 2, 3, 1, 2, 3 trihydroxybenzene, and the general name for this is pyrogallol, and another example is 1, 3, 5. Okay. So, this is correct, this is fifth position, and here also. So, the structure of OH is at fourth position, and here they have written it in third, means they have nomenclature this as 1, 3. Okay. So, this OH should be in the third position, otherwise if it is there only, then we have to nomenclature this as 1, 4, 5 trihydroxybenzene. Okay. And this is generally called as fluoroglucinol. Okay. So, fluoroglucinol is the general name of this phenol. Okay. So, there are so many mistakes in the PPT. So, this is a ChemDraw file, so I could not correct it. So, I am explaining it here only. Okay. There is a mistake, that means this is in the fourth position. So, this phenol's name has to be 1,4-dihydroxybenzene, and it is generally called as quinol. Okay. So, here in the same way, so this is in the fourth position, but here it has been written as 1, 3. No, this is 1, 4, 1, 4, 5 trihydroxybenzene. Okay. So, in this way we are going to classify phenols based on the number of phenol units or based on the number of OH groups attached to the aromatic ring, okay. And it continues, so it might be a 4 phenol also could be present, or 5 is also could be present, okay. And next topic what we have to discuss is acidic properties of phenols. So, phenols are more acidic than typical alcohols, okay. So, why I am comparing this with alcohols is, so OH what we are seeing is this is a functional group of alcohols, right. We all know that the functional group of alcohol is OH. So, here compared to the alcohols, phenols are more acidic. The acidity of the hydroxyl group in phenol is commonly intermediate between that of aliphatic alcohols and carboxylic alcohols, okay. So, this we have to keep it in mind. So, the pKa value of these aliphatic alcohols and carboxylic alcohols will be usually between 10 and 12. So, the deprotonation, so this is what the deprotonation here, the in the hydroxylic group, what happens is, so when it comes in contact with the water, or when phenols are mixed or converted into the solutions, so here protonation is going to takes place. The deprotonation of a phenol forms a corresponding negative phenolate ion, or it is also called as a phenoxide ion, okay. So, this is what is called as a phenoxide ion, or it is also called as phenolate, and the corresponding salt are called as phenolates or phenoxides, okay. So, it is also called as aryl oxide according to the IUPAC gold book. So, we call it as aryl oxide, okay. So, here to make it simplification, so let me call it as a phenoxide ion itself, okay. So, aryl oxide is because the benzene ring is also called as aryl ring. So, that is why aryl oxide. So, here phenol it is also can be understood as a benzene, okay. So, phenoxide means so it is an ion, phenoxide is an ion which has been formed due to the deprotonation of hydrogen which was present in the phenol, and thereby converting it into a ion which is called as a phenoxide ion, okay. So, what happens when we treat it with the NaOH? Okay, so NaOH is a base. So, by studying this, by taking this example, we can understand the acidic properties of phenols in a better way. So, as I said, so phenols when they react with the water molecules, so they are going to get converted into the ions. One is a proton which will be in the form of H plus and phenoxide ion will be formed, okay. Phenols when we react with alkali metal hydroxides, say for example sodium hydroxide is an example of alkali metal hydroxide. So, what is the product formed is, so we are going to get salts, that salt is one is sodium phenoxide ion, okay. So, here what happens when phenol is reacted with the sodium hydroxide. So, here also, so here OH is missing. So, this is benzene, this is not phenol, okay. So, just see this structure. So, in phenol when it reacts with the alkali metal hydroxide, so we are going to get sodium phenoxide ion, okay. So, here O minus Na plus is formed, okay. So, the stability of phenoxide ion is due to the resonance, okay. So, here just like how we study the resonance structures of benzene, in the same way in phenols also. So, when phenols combine with sodium hydroxide or any such alkali metal hydroxide, so their sodium phenoxide is going to form. So, that sodium phenoxide is more stable just like benzene, and the stability of phenoxide ion is due to the resonance, okay. So, the negative charge on the oxygen of the phenoxide ion is delocalized through resonance structures. Okay, so these are the different resonance structures, just like how we observe in case of benzene. So in the same way, so here the rearrangement of bonds in the phenol is going to takes place. So this is a clear representation of resonance stabilization of phenoxide ion. Okay, and due to this property, due to the resonance which is absorbed in case of phenols, so the stability of the phenoxide ion is more. Okay, so this could be attributed to the reason why phenols are more acidic than compared to the alcohols. Okay. So, phenols are acidic in nature due to the formation of stable phenoxide ions in aqueous solution. Okay. In aqueous solution, when phenols comes in contact with aqueous solution, so they are more stable, and that stability is because of the formation of phenoxide ions, and those phenoxide ions represents the similar way of resonance stabilization, just like how we will see for benzene. Okay. So, these are the different resonance stabilizations or resonance form of phenoxide ions, starting from this 6th structure to the 10th structure. Various different types of resonance forms could be observed in case of phenols. Okay. So, this is all about acidic properties of phenols. And next is we have to concentrate on the comparison of acidic properties of phenols with alcohols. Okay. So, as I said, so the phenols are more acidic compared to the alcohols. The alcohol and alkoxide ion can each be represented satisfactorily only by a single structure. Okay, so here I have taken only one single structure, and I am representing the alcohol and alkoxide ion in each case. But the phenol and phenoxide ion are resonance hybrids of more than one structures. Okay, so that is if we see from structure 1 to 5. Okay, so here if you see the structures 1 to 5, and if we observe the structures of 6 to 10 respectively. So, this is structures. Okay. So, then we can clearly understand that the dipolar structure, that is this one, the third structure. So, here this is called as dipolar structure because so in this structure we can see both positive and negative attributes which are present. Okay. So, the dipolar structure 3 and 5 for the phenol are less stable than the structures 8 to 10 for the phenoxide ion. Okay. So, this is the comparison of acidic properties of phenols, and this is the comparison of acidic properties of phenols with alcohols. Okay. So, here we have to make 2 points. When we compare the acidic properties of phenols with alcohols, so what is the structure of alcohols and alkoxide ions? Okay. So, what is meant by alkoxide ion? When alcohols are combined with the aqueous solution, alkoxide ion is formed. Okay. When alcohols are reacted with aqueous solution, alkoxide ions are formed. When phenols are reacted with aqueous solution, phenoxide ions are formed. Okay. So, this is the difference between alkoxide and phenoxide ions. So, alkoxide ions can be represented only by single structure, whereas phenol and phenoxide ions, so they have resonance hybrids which are more than one structures, Okay. So, for this reason, since phenoxide or phenols have more structures, so phenoxide ion is stabilized to a greater extent than the phenol. So, this favors the ionization of phenols to a larger extent compared to alcohols. Hence, Ka value of a phenol is larger than that of alcohol. That is why I said in the beginning. So, phenols are more acidic than compared to the alcohols. Okay. Next is about comparison of acidic properties of phenols with carboxylic acids. The carboxylic acids undergo dissociation to give carboxylate anion and proton. Okay. So, this is how the dissociation of carboxylic acid is going to take place. So, when carboxylic acid comes in contact with the aqueous solution, so this is carboxylate ions and this is the one proton which is going to be separated and thereby it forms a dissociated form of carboxylic acid. Okay. So, this is carboxylic acid. When this carboxylic acid comes in contact with aqueous solution, so the here in this OH, so one hydrogen which is present, so it will get separated thereby forming here O minus and H plus. So, this is how it is going to get dissociated. So, both the carboxylic acid and carboxylate ions they have resonance hybrids. Okay. So, both carboxylate ions and carboxylic acid, so both can be represented in terms of resonance hybrids. So, how we write the resonance hybrid is, so here if we observe the structure 13 and 14, okay. So, here since there is two lone pair of electrons which is present in the oxygen. So, they indulge in the resonance form. So, here the double bond will be converted into the single bond and since there is a lone pair of electron which is present in this oxygen, that will return to this bond, thereby forming or converting it into a double bond. Okay. So, here this structure 14, so this is a resonance hybrid structure of carboxylic acid. Okay. So, in this way this carboxylate anion and carboxylic acid, so they both undergo or they both can be represented in terms of resonance hybrids as shown here. Okay. So, the structure 11, okay. So, if we observe the structure 11, so this is the structure 11. Okay, here the number is missing. This is the structure of carboxylic acid and the dipolar structure. So, this is the dipolar structure. Okay. So, suppose if it is if hydrogen is present here, definitely here we will get a negative sign and here we will get a positive sign. So, that is why it is called as dipolar structure. For the carboxylic acids are much less stable than the equivalent structures. So, these two are the equivalent structure. Here if you see the structure 13 and structure 14. So, they are the equivalent structures for the carboxylate ions or anions, it also can be called as anion because so carboxylate ions are always they carry a negative sign, that is because when dissociation occurs, so here the hydrogen which is going to get separated, so the hydrogen will be converted into a proton, that means always it will have a positive charge. So, that is why the carboxylate ions always will be anions. This accounts for the acidity of the carboxylic acids. The phenoxide ions is resonance stabilized to a greater extent than phenol. So, the phenoxide ions they are resonance stabilized, that is because in the previous slide we saw. So, the phenoxide ion exists in various different types of resonance hybrids. We can assign more than one structure for phenoxide ions. Okay. And unlike the carboxylate ions, so this structure 13 and 14, so phenoxide ion resonance structure that is 6 and 10 are not equivalent. Okay. So, this it is difficult for me to show in the slides because you may get confused. So, that is why I request and suggest you to keep the textbook in front of you while listening to this explanation and observe the structures as I say structure 6 to 10. Okay. So, this structure 6 to 10 is the resonance stabilization or resonance hybrids of phenoxide ions. So, they are not equivalent. Okay. So, this you can see it in your textbook and if you get any doubts you can clarify it when you come to the college along with the book, or I can use blackboard and understand you how the phenoxide ion resonance structures are not equivalent. So, this makes Okay. So, since the carboxylate anion structures that is the structure 13 and 14, which compared to the phenoxide ion resonance structure, that is from structure 6 to 10, are not equivalent. So, this makes the hybrid of a carboxylate ion relatively more stable than the hybrid of a phenoxide ion. Hence, carboxylic acids is more acidic, that means it has got higher Ka value than phenols. Okay. This is how we are going to understand the comparison of acidic properties of phenols with carboxylic acids. Next is a comparison of acidic properties of phenols with carbonic acids. The ionization of carbonic acid may be represented in this way. When water combines with carbon dioxide, we get carbonic acid, and this is the structure of carbonic acid. Okay. So, when water combines with carbon dioxide, this is carbon dioxide, this is water H2O. Okay. So, two molecules of water molecules are there. So, need not to worry about balanced equations here, reaction, do not worry about balance, just observe how the carbonic acid is going to get formed. Okay. So, when water combines with carbon dioxide, we get carbonic acid, and this is converted into bicarbonate ion when this carbonic acid comes in contact with the aqueous solution. Okay. So, the carboxylate ion of carbonic acid has two equivalent contributing structures. What are those two equivalent contributing structures? So, this is if you see structure 15 and 16. So, these two are two equivalent contributing structures. So, this makes carbonic acid a fairly strong acid. Since the hybrid of phenoxide ion does not contain such equivalent resonance structure, so it is less stable than the hybrid of bicarbonate ion of carbonic acid. Okay. So, due to this reason, carbonic acid is a stronger acid than phenol. Okay. So, this is what about the comparison of acidic properties of phenols with carbonic acids. So, in this session I tried giving you a brief introduction about what is meant by phenols, and thereby we saw how we are going to classify phenols, based on the number of hydroxyl groups present or attached directly to the benzene ring or aromatic ring. And next we saw some acidic properties of phenols. So, we compared the acidic properties of phenols with alcohols and carboxylic acids and carbonic acids. Okay. So, I am going to stop it here, and in my next class we will see some important reactions and their mechanisms in detail. Okay. So, these reactions and reaction mechanisms which are derived by taking a starting material as a phenol derivative. Okay. So, since this is the chapter which says about the reactions and reactivity of phenols, so definitely we will study some interesting reactions in organic chemistry in which we are going to use phenols or the derivatives of phenols in various applications. Okay. So, how we are going to synthesize acetophenone compounds or phenols or benzaldehyde, how phenol can be converted into benzaldehyde. So, in this way we will see some important organic reactions in detail in my next class. Okay. So, thank you dear students.